Welcome back. It's Saturday. Let's try reading some more. I'd like to read about history of the transistors. We have here, but I need a little cola. So I got up 9 a.m. today and I make my morning video. Looking my game now, it's soon 1 p.m. I need a sour saving. I need a shower saving a lot. I need to do this today. I have two fresh blades left. This one starts to get old. That's some old one I'm saving. But I need some cola. I got YouTube money yesterday, so I have a little cola again. But I have to wait 6 days for my pension. But I buy a little more food and bread and stuff. Snack. Got a little chocolate for later tonight. Got some biscuits. 1 can more of chili con carne. Oops, that's too much. I forgot that I cannot drink all this. That's way too much cola. So we need to put it back. But let's drink it. But I need a little break. Little have super cheap potatoes tomorrow and carrots. That was too much cola. I need to put. Let's read. So that's so much I like to read. But how I should finish that, I don't know. But let's read this. Good. Then I will go to my bed and read this. So I just read one by one. Just try to learning something new and have a good day.
History of the transistor. This article may misquote or misrepresent many of its sources. Please see the cleanup page for more information. Editors. Please remove this warning only after the diffs listed. Wikipedia talk requests for comment /jagged85 subpage here have been checked for accuracy. August 2022. A transistor is a semiconductor device with at least 3 terminals for connection to an electric circuit. In the common case, the third terminal controls the flow of current between the other 2 terminals. This can be used for amplification, as in the case of a radio receiver, or for rapid switching, as in the case of digital circuits. The transistor replaced the vacuum tube triad, also called a thermionic valve, which was much larger in size and used significantly more power to operate. The first transistor was successfully demonstrated on the 23rd of December, 1947, at Bell Laboratories in Murray Hill, New Jersey. Bell Labs was the research arm of American Telephone and Telegraph, AT&T. The 3 individuals credited with the invention of the transistor were William Shockley, John Bardeen and Walter Brattain. The introduction of the transistor is often considered one of the most important inventions in history. Transistors are broadly classified into 2 categories: bipolar junction transistor, BJT, and field effect transistor, FET. The principle of a field effect transistor was proposed by Julius Edgar Lilienfeld in 1925. John Bardeen, Walter Brattain and William Shockley invented the first working transistors at Bell Labs, the point contact transistor in 1947. Shockley introduced the improved bipolar junction transistor in 1948, which entered production in the early 1950s and led to the first widespread use of transistors. The MOSFET was invented at Bell Labs between 1955 and 1960. MOSFETs use even less power, which led to the mass production of MOS transistors for a wide range of uses. The MOSFET has since become the most widely manufactured device in history. Origins of transistor concept, edit. The first patent for the field effect transistor principle was filed in Canada by Austrian-Hungarian physicist Julius Edgar Lilienfeld on the 22nd of October, 1925, but Lilienfeld published no research articles about his devices, and his work was ignored by industry. In 1934, German physicist Dr. Oskar Hale patented another field effect transistor. There is no direct evidence that these devices were built, but later work in the 1990s show that one of Lilienfeld's designs worked as described and gave substantial gain. Legal papers from the Bell Labs patent show that William Shockley and a co-worker at Bell Labs, Gerald Pearson, had built operational versions from Lilienfeld's patents, yet they never referenced this work in any of their later research papers or historical articles. The Bell Labs work on the transistor emerged from wartime efforts to produce extremely pure germanium crystal mixer diodes, used in radar units as a frequency mixer element in microwave radar receivers. UK researchers had produced models using a tungsten filament on a germanium disc, but these were difficult to manufacture and not particularly robust. Bell's version was a single crystal design that was both smaller and completely solid. A parallel project on germanium diodes at Purdue University succeeded in producing the good quality germanium semiconducting crystals that were used at Bell Labs. Early tube-based circuits did not switch fast enough for this role, leading the Bell team to use solid-state diodes instead. After the war, Shockley decided to attempt the building of a triad-like semiconductor device. He secured funding and lab space, and went to work on the problem with Bardeen and Brattain. John Bardeen eventually developed a new branch of quantum mechanics known as surface physics to account for the odd behavior they saw, and Bardeen and Walter Brattain eventually succeeded in building a working device. The key to the development of the transistor was the further understanding of the process of the electron mobility in a semiconductor. It was realized that if there was some way to control the flow of the electrons from the emitter to the collector of this newly discovered diode, discovered 1874, patented 1906, one could build an amplifier. For instance, if one placed contacts on either side of a single type of crystal, the current would not flow through it. However, if a third contact could then inject electrons or holes into the material, the current would flow. Actually doing this appeared to be very difficult. If the crystal were of any reasonable size, the number of electrons, or holes, required to be injected would have to be very large, making it less useful as an amplifier because it would require a large injection current to start with. That said, the whole idea of the crystal diode was that the crystal itself could provide the electrons over a very small distance, the depletion region. The key appeared to be to place the input and output contacts very close together on the surface of the crystal on either side of this region. Brattain started working on building such a device, and tantalizing hints of amplification continued to appear as the team worked on the problem. Sometimes the system would work, but then stop working unexpectedly. In one instance, a non-working system started working when placed in water. The electrons in any one piece of the crystal would migrate about due to nearby charges. Electrons in the emitters, or the holes in the collectors, would cluster at the surface of the crystal, where they could find their opposite charge floating around in the air, or water. Yet they could be pushed away from the surface with the application of a small amount of charge from any other location on the crystal. Instead of needing a large supply of injected electrons, a very small number in the right place on the crystal would accomplish the same thing. Their understanding solved the problem of needing a very small control area to some degree. Instead of needing two separate semiconductors connected by a common, but tiny, region, a single larger surface would serve. The emitter and collector leads would both be placed very close together on the top, with the control lead placed on the base of the crystal. When current was applied to the base lead, the electrons or holes would be pushed out, across the block of semiconductor, and collect on the far surface. As long as the emitter and collector were very close together, this should allow enough electrons or holes between them to allow conduction to start. An early witness of the phenomenon was Ralph Bray, a young graduate student. He joined the germanium effort at Purdue University in November 1943 and was given the tricky task of measuring the spreading resistance at the metal semiconductor contact. Bray found a great many anomalies, such as internal high resistivity barriers in some samples of germanium. The most curious phenomenon was the exceptionally low resistance observed when voltage pulses were applied. This effect remained a mystery because nobody realized, until 1948, that Bray had observed minority carrier injection, the effect that was identified by William Shockley at Bell Labs and made the transistor a reality. Bray wrote, "That was the one aspect that we missed. But even had we understood the idea of minority carrier injection, we would have said, oh, this explains our effects. We might not necessarily have gone ahead and said, let's start making transistors, open up a factory and sell them." At that time the important device was the high back voltage rectifier. Shockley's research team initially attempted to build a field effect transistor, FET, by trying to modulate the conductivity of a semiconductor, but was unsuccessful, mainly due to problems with the surface states, the dangling bond, and the germanium and copper compound materials. In the course of trying to understand the mysterious reasons behind their failure to build a working FET, this led them to instead inventing the bipolar point contact and junction transistors. First working transistor, edit. The Bell team made many attempts to build such a system with various tools, but generally failed. Setups where the contacts were close enough were invariably as fragile as the original cat's whisker detectors had been, and would only work briefly, if at all. Eventually they had a practical breakthrough. A piece of gold foil was glued to the edge of a triangular plastic wedge, and then the foil was sliced with a razor at the tip of the triangle. The result was two very closely spaced contacts of gold. When the plastic was pushed down onto the surface of a crystal and voltage applied to the other side, on the base of the crystal, current started to flow from one contact to the other as the base voltage pushed the electrons away from the base towards the other side near the contacts. The point contact transistor had been invented. From Walter Britton's laboratory notebook entry of the 15th of December, 1947, when the points were very close together, got voltage amp about 2 but not power amp. This voltage amplification was independent of frequency 10 to 10,000 cycles. And in the 16th of December, 1947 notes, using this double point contact was made to a germanium surface that had been anodized to 90 volts, electrolyte washed off in H2O and then had some gold spots evaporated on it. The gold contacts were pressed down on the bare surface. Both gold contacts to the surface rectified nicely. The separation between points was about 4x 10 cm. One point was used as a grid and the other point as a plate. The bias, DC, on the grid had to be positive to get amplification. Power gain 1.3, voltage gain 15 on a plate bias of about 15 volts. Brattain and H.R. Moore made a demonstration to several of their colleagues and managers at Bell Labs on the afternoon of the 23rd of December, 1947, often given as the birth date of the transistor. The PNP point contact germanium transistor operated as a speech amplifier with a power gain of 18 in that trial. In 1956, John Bardeen, Walter Hauser Brattain, and William Bradford Shockley were honored with the Nobel Prize in Physics for their researches on semiconductors and their discovery of the transistor effect. 12 people are mentioned as directly involved in the invention of the transistor in the Bell Laboratory. At the same time, some European scientists were led by the idea of solid-state amplifiers. The German physicist Herbert F. Matter, 1912-2011, had conducted experiments at Telefunken with what he called duodiode, double diode, from 1942, when he first observed transconductance effects with silicon diodes manufactured for German radar equipment for World War II. Finally, on the 13th of August, 1948, Matter and Heinrich Welker, 1912-1981, working at Compagnie des Frames et Signals Westinghouse in Aulnay-sous-Bois, France, applied for a patent on an amplifier based on the minority carrier injection process which they called the transistron. The device was shown publicly on the 18th of May, 1949. Transistrons were commercially manufactured for the French telephone company and military, and in 1953 a solid-state radio receiver with 4 transistrons was demonstrated at the Dusseldorf Radio Fair. As Bell Labs did not make a public announcement of their transistor before June 1948, the transistron was an independent parallel discovery and development. Etymology, edit. Bell Telephone Laboratories needed a generic name for the new invention. Semiconductor triad, surface states triad, crystal triad, solid triad and iotatron were all considered, but transistor, coined by John R. Pierce, was the clear winner of an internal ballot, owing in part to the affinity that Bell engineers had developed for the suffix "ister." The rationale for the name is described in the following extract from the company's technical memorandum calling for votes. Transistor. This is an abbreviated combination of the words transconductance or transfer, and varistor. The device logically belongs in the varistor family, and has the transconductance or transfer impedance of a device having gain, so that this combination is descriptive. Bell Telephone Laboratories, Technical Memorandum, the 28th of May, 1948. Pierce recalled the naming somewhat differently. The way I provided the name was to think of what the device did. And at that time, it was supposed to be the dual of the vacuum tube. The vacuum tube had transconductance, so the transistor would have transistance. And the name should fit in with the names of other devices, such as varistor and thermistor. And I suggested the name transistor. John R. Pierce, interviewed for PBS show Transistorized. The Nobel Foundation states that the term is a combination of the words transfer and resistor. Early conflict, edit. Shockley was upset about the device being credited to Brattain and Bardeen, who he felt had built it behind his back to take the glory. Matters became worse when Bell Labs lawyers found that some of Shockley's own writings on the transistor were close enough to those of an earlier 1925 patent by Julius Edgar Lilienfeld that they thought it best that his name be left off the patent application. Improvements in transistor design, edit. Switch to silicon, edit. Germanium was difficult to purify and had a limited operational temperature range. Scientists theorized that silicon would be easier to fabricate, but few bothered to investigate this possibility. Morris Tannenbaum et al. At Bell Laboratories were the first to develop a working silicon transistor on the 26th of January, 1954. A few months later, Gordon Teal, working independently at Texas Instruments, developed a similar device. Both of these devices were made by controlling the doping of single silicon crystals while they were grown from molten silicon. A superior method was developed by Morris Tannenbaum and Calvin S. Fuller at Bell Laboratories in early 1955 by the gaseous diffusion of donor and acceptor impurities into single crystal silicon chips. Up until the late 1950s, however, germanium remained the dominant semiconductor material for transistors and other semiconductor devices. Germanium was initially considered the more effective semiconductor material, as it was able to demonstrate better performance due to higher carrier mobility. The relative lack of performance in early silicon semiconductors was due to electrical conductivity being limited by unstable quantum surface states, preventing electricity from reliably penetrating the surface to reach the semiconducting silicon layer. Silicon surface passivation, edit. Main article, surface passivation. See also, thermal oxidation. Surface passivation, the process by which a semiconductor surface is rendered inert, and does not change semiconductor properties as a result of interaction with air or other materials in contact with the surface or edge of the crystal, was first discovered by Carl Frosk and Lincoln Derrick at Bell Labs between 1955 and 1957. Frosk and Derrick showed that a silicon dioxide, SiO2, layer protected silicon wafers against the environment, masked against dopant diffusion into silicon and electrically insulated, and demonstrated it by creating the first silicon dioxide transistors, the first transistors in which drain and source were adjacent at the surface insulated by a SiO2 layer. Planar process, edit. Main articles, planar process and planar transistor. Jean Huerny was aware of the work done by Frosk and Derrick at Bell Labs. Later, Huerny attended a meeting where Mohammed M. Attala presented a paper about passivation based on the previous results at Bell Labs. Taking advantage of silicon dioxide's passivating effect on the silicon surface, who only proposed to make transistors that were protected by a layer of silicon dioxide and issued a first patent in 1959, while working at Fairchild Semiconductor. MOSFET, edit. Main article, MOSFET. In 1959, the MOSFET was introduced by a Bell Labs team under Mohammed M. Attallah and Dewan Khan. As of 2020, it was still the dominant transistor type in use, with an estimated total of 13 sextillion, 1.310, MOSFETs manufactured between 1960 and 2018. The key advantages of MOSFET transistors over BJTs are that they consume no current except when switching states and they have faster switching speed, ideal for digital signals. Early commercialization, edit. The world's first commercial transistor production line was at the Western Electric plant on Union Boulevard in Allentown, Pennsylvania. Production began on the 1st of October, 1951 with the point-contact germanium transistor. The first commercial application of transistors in telecommunication was in the fall of 1952 in tone generators for multi-frequency signaling of the number 5 crossbar switching system in the Inglewood, NJ installation, used for the first field trial of direct distance dialing, DDD. By 1953, the transistor was being used in some products, such as hearing aids and telephone exchanges, but there were still significant issues preventing its broader application, such as sensitivity to moisture and the fragility of the wires attached to germanium crystals. Donald G. Fink, Philco's Director of Research, summarized the status of the transistor's commercial potential with an analogy: is it a pimpled adolescent, now awkward, but promising future vigor? Or has it arrived at maturity, full of languor, surrounded by disappointments? Semiconductor companies initially focused on junction transistors in the early years of the semiconductor industry. However, the junction transistor was a relatively bulky device that was difficult to manufacture on a mass production basis, which limited it to a number of specialized applications. Transistor radios, edit. Main article, Transistor radio. Prototypes of all transistor and radio receivers were demonstrated, but were really only laboratory curiosities. However, in 1950 Shockley developed a radically different type of solid-state amplifier which became known as the bipolar junction transistor, which works on a completely different principle than the point-contact transistor. Morgan Sparks made the bipolar junction transistor into a practical device. These were also licensed to a number of other electronics companies, including Texas Instruments, who produced a limited run of transistor radios as a sales tool. Early transistors were chemically unstable and only suitable for low-power, low-frequency applications, but as transistor design developed, these problems were slowly overcome. There are numerous claimants to the title of the first company to produce practical transistor radios. Texas Instruments had demonstrated all transistor and radios as early as 1952, but their performance was well below that of equivalent vacuum tube models. A workable all-transistor radio was demonstrated in August 1953 at the Dusseldorf Radio Fair by the German firm Intermetal. It was built with 4 of Intermetal's handmade transistors, based upon the 1948 invention of Herbert Matter and Heinrich Welker. However, as with the early Texas units, and others, only prototypes were ever built. It was never put into commercial production. The first transistor radio is often incorrectly attributed to Sony, originally Tokyo Zushin Kogyo, which released the TR-55 in 1955. However, it was predated by the Regency TR-1, made by the Regency Division of IDEA, Industrial Development Engineering Associates, of Indianapolis, Indiana, which was the first practical transistor radio. The TR1 was announced on the 18th of October, 1954, and put on sale in November, 1954 for $49 and 95 cents, the equivalent of about $500 in year 2000 and $20, and sold about 150,000 units. The TR1 used 4 Texas NPN transistors and had to be powered by a 22.5 volt battery, since the only way to get adequate radio frequency